that. All right, there we go.
Don't worry, I'll keep track for you.
Thank you.
Gee, they're getting rid of FFmpeg.
They are?
Yep. They're going to AVConf.
They're going to
AVConf. C-O-N-P. A-V-C-O-N-P.
AVConf.
Yeah.
Is it still done by the same people? Probably.
Well, you know, it's just an offshoot of FFmpeg. FFmpeg's no longer maintained.
Oh,
All the
okay.
maintainers went to
So it's a
AVConf.
branch, basically.
Right.
Okay.
But AVConf does this. It has the exact same commands.
Ah, okay.
It's just different.
But I just need to make a macro. All right. So these are the solutions, already, figured out. So we'll go over all of the questions today, but some of the questions I'll only go over one of the many different one of the three alternatives, and then the only one left, would be question number, the last one, which I'll only use one single case. All right. So let's go ahead and take a look. I am in the process of grading the exam, but I'm still trying to determine how to do the scoring, because instead of giving you a single number, as I talked about a little bit earlier, I want to tie this in to student learning outcomes. In other words, for each thing that I'm supposed to teach, there will be a score for that. So when you look at a score, it is not just a number to say, oh, you're doing okay in the class, or you're doing really well in the class. It will tell you you are understanding this concept correctly, you're understanding this concept correctly, you're understanding this concept correctly. So when you look at the score, it tells you exactly if there's anything you need to do, what you need to do. Okay, what topic do you need to go over again, or read the notes again, or try to understand better. So I'm trying to use the tool in Moodle to do that. So are there any questions about that part? No question? Does any class do that, in your other classes where the number is tied into student learning outcomes? Kind of. So I'm going to use Moodle to kind of, this is the first semester I'm trying to use that tool that way. So it might take a little bit longer for me to set up the tool, but once it is set up, I think it will be beneficial. All right, so this is the first version of question number 1. We have to trace a particular program. And in this case, I don't want to kind of break it up because it's really a short trace to begin with. So I want to just trace the entire program. And here is the answer. I can actually magnify this a little bit more because the question itself is not important. It is really just this part that is important. This is one of the variants. The precondition is x has a value of 3, y has a value of 6. The first line we have to execute is line 1. We cannot skip to line 2 or the other lines. We have to start with line 1. On line 1, we are doing a single comparison. We are evaluating a condition. The condition in this case is x is less than y. In other words, is it true or is it false? The answer is it is true that x is less than y. As a result, we have to go to the then portion of the outer conditional statement. The then portion of the outer conditional statement is going from line 2 to line 6. So the next line we execute is line 2. Line 2 has another condition to evaluate. In this case, is whether x is less than 3. X has a value of 3. 3 is not less than 3. So 3 is less than 3 is false on line 2. Because this condition is false, we cannot execute line 3. We have to skip to line 5. Line 5 executes, it changes the value of z to 2. When this is all done, we get to the end of the inner conditional statement. But the inner conditional statement is the only condition in the then part of the outer conditional statement, which means there's absolutely nothing to do after that. And that's why we skip all the way to post. Are there any questions about this particular question? You thought this a quick question? Let's take a look at a picture, a pictorial representation of this logic. Okay, so this part is hard to capture on the screen. So if you want to take a picture of this, that's fine with me. Okay, so the outer conditional statement is a conditional statement. Okay, this is running out of ink, and I have to be careful. Last time I used a permanent marker. Yeah, that wasn't very smart. Okay, there we go. This one is a little better. Just have to draw slower. Okay, so this is a conditional statement. Let's say this is the outer conditional statement, which is line 1, line 7, and line 13. Okay? The shape of a conditional statement is always like this. Is that okay so far? So the question we have to ask to determine which side to go is x is less than y. Okay, so x is less than y. If it is true, we go to the left-hand side. If it is false, we go to the right-hand side. Are we doing okay so far? So this is representing the construct, which is basically our line 1, line 7, and line 13. Okay. Now when you look at line 2 to line 6, which is the inner conditional statement for the then portion of the outer conditional statement, you are basically drawing another conditional statement inside the bigger one. Oops. Like that. So this one has a different question. The question to ask here is x is less than 3. If that is true, we go to this side. If it is false, we go to the other side. Is that okay? If that is true, we go to line 3. This is basically line 3. Z gets a value of 1. If it is false, we go to the other side, which is line 5. Z gets a value of 2. Are we still doing okay? So when we trace this algorithm, starting with x equals 3 and y equals 6, x is less than y is true. So we go to this side. We go to the left-hand side. But once we get into this part here, we have to answer another question to decide which way to go. X is less than 3 is the condition. In this case, x has a value of 3, so x is less than 3 is false. And that's why we follow the right side here. We execute this statement, which is z gets 2. And then what do? We get out of the inner conditional statement, and there's nothing else to do. So we have to get out of the outer conditional statement as well. Now, in your trace, if you indicate, trace the tracing of line 6 or line 12 or line 13, I won't take any points off, okay? Because those are not, they don't really do anything. So if you say that you're stepping onto those lines, it's not a problem. Any other questions about number 1? No questions? Okay. So this part definitely has to do with how things are nested, and when things are nested, how do we follow the trace? The next one is also kind of nesting, but in this case it's a loop. This is the trace. The first line was given. X is less than y is true because x has a value of 5, y has a value of 11 on line 34. And because it is true, we have to go inside the loop. Inside the loop, we have a single conditional statement starting on line 35, ending on line 39. On line 35, we have to evaluate the condition x equals 5. In the first iteration, x does equal to 5, so x equals 5 is true. When the condition is true, we have to go to the then branch, which is on line 36. Line 36 is just assigning, changing the value of x to 10. And then after that, we have nothing else to do in the loop. So as a result, we get out of the inner conditional statement, and then we hit end while. But because this is a loop, when we are done with one iteration, we have to go back to the beginning. And that's why the next line is the line 34. Line 34, once again, is evaluating x is less than y. It is still true because x has a value of 10, y has a value of 11. 10 is less than 11 is true. We have to go in again into the conditional statement. X equals 5 is false because x now has a value of 10, not 5 anymore. So we have to go to the else part of the conditional statement, which is on line 38. Line 38 is just adding 1 to x. X had a value of 10, now it is 11. After line 38, we exit from the inner conditional statement. There's nothing else to do there. And then we go back to the beginning of the while loop. The condition of x is less than y is finally false because 11 is less than 11 is false, and that's how we can get to line 41, because that is whatever is following this particular code. Are there any questions about this one? Does anyone want me to draw the picture? Yep.
You don't have to put a post onto this, right?
There's no post because I kind of talked about it in the class, and kind of in the instruction I said there's use line 41 to indicate that this code here is done. If you use post, I won't take any points off. Okay. But are there any questions about this? Does anyone want me to kind of draw this as a picture, or you guys are good with that? Good. Okay. Any other questions? Yep.
Is this all being recorded?
This is all being recorded except for the part that is on the whiteboard. Yep. Probably use a cell phone to take a picture of this. I don't have anything that can display. You know what? A USB webcam is what I need. And I used to have one too. I just did not bring it today, because that way I can just bring up the image from the USB webcam. Just show it once so it appears on the monitor, then it will be captured. But I just don't have that capability right now. All right, so this is the last one. The last one of page 1. Question number 3. Once again, we want to figure out when we can make each condition happen. In other words, how can we make z equal to 1 after this code? How can we make z equals 2, and so on? Okay, so we'll deal with the first case first. How do we make z gets 1? Well, this condition has to be true. How can we make x equals y and x equals 3? Well, they all have to be 3. So when x is 3, y is 3, then z will get a value of 1. The comment part, you don't have to do anything except for the impossible, and then you have to explain why they are impossible. The second case is when z gets a value of 2. Well, to make that happen, x has to equal to y. But now we have one little restriction. What is it? X cannot equal to 3, because if x does equal to 3, it would have executed line 2, and we would not have a chance. We would not have a chance to evaluate the condition on line 3 to begin with. So you have to make x equal to y to make z equal to 2, but you cannot pick the value 3 anymore. Are we still doing okay so far? Okay. What about making z equal to 3? Well, that means the condition of line 1 has to be false. The condition of line 2 also has to be false, but the condition of line 5 has to be true. Well, that really means x equals y is completely out of the picture, because that is already covered by by condition 1, by the condition of line 1 and the condition of line 3. So we can only make x less than y in this case. As long as you can make x less than y, it will work. In this case, if I make x equal to 3 and y equal to 4, we'll make that work. Number 7. Now, number 7, line 7 is a tricky one. In other words, how can we make x equal to 4 using this logic? X cannot equal to y, and because of line 5, x cannot be less than y either. So by the time we get to line 7, to make all the other conditions false, but only the condition of line 7 true, x has to be greater than 7 at that point. Okay? But you can pick any value. You can pick any pair of value. As long as x is greater than y in this case, it will still work. So I just picked the easy one, which is making x 4 and making y 3. That will work. By the time we get to line 9, it means the conditions specified on line 1, line 3, line 5, and line 7, they all have to be false, and the condition of line 9 has to be true to make this happen. It is now impossible because the negation of all of those will include x is greater than y. And as a result, there's no way by line 9 that we will still have x greater than y, and as a result, it is not possible. Any questions about this one? Because this is really the trickier one. No questions? Okay. So when we get to line 12, making z equal to 6, it's just not possible. Because we covered all the cases already. x equal to y, x is less than y, x is greater than y. They're all covered already. There's nothing else that we can use to make the program go to line 12. Yep.
My reasoning, I put that since line 3 x is equal to y, and then line 7 x cannot be y, because of those two makes any other choice impossible.
You can argue with that too. Yep. But the bottom line is, you need to make all of the conditions prior to line 11. They all have to be false. You have a big conjunction of every single one negated, and that is not possible. You don't have to prove to me that it is not possible, because I don't want Boolean algebra to be one of the things that you have to do. But intuitively, you kind of have to just say that it is not possible because all the cases are already covered. Okay. Any questions about number 3? No questions? All right. So that's 1. Take a look at. Do you want me to go through all the variations, or do you think you're fine with going over one variation? The other ones are pretty much the same thing. Okay, I'll just show you one variation because the next one is pretty close. This one, I just have a different initial value, and I think the comparison goes in a different way too. I might have changed the how the comparison happens. Instead of x is less than y, it is x is greater than y. But other than that, it's the same construct. It's the same structure. So is that okay, or does anyone want me to go over this one? No, not particularly. Okay. What about this one? Question number 2. Pretty much the same thing. It's just that I start with a value of 3, and y starts with a value of 9, and I check for 3, make it turn to 8, and add 1 in the code. So if you follow the logic, it actually has the same sequence of line numbers. It's just that the value of x is changed slightly differently. Okay. Any questions about this one? Yeah. Okay. And this one is, for the most part, the same thing too. I might have flipped x is less than y versus x is greater than y. In fact, I think this one I did not make any changes, did I? Looked about the same to me.
I think 5 and 3 were switched on the other one.
5 and 3 are switched. Okay, that might be. Yeah, you're right. Those two are switched, which has no effect to things that are after that. Yep. Go ahead. Oh, okay. All right. So this is the second variant, and then here comes the third one. So once again here, instead of a less than, I have a less than or equal to. And then over here, we are just starting with a different value. Well, y has a different value, and then x got incremented by 2 instead of by 1. But the flow of the logic will be identical to the other two cases. So we'll still have the same line number trace. It's just that the value that x has throughout time is changed a little bit. And then for the last question, let's see how I switch. Yeah, for this one I switched the x is greater than y versus the x is less than y. So those two are switched. Any questions about this one? Okay, so they are pretty much the same thing. If you know the solution to one, the other ones should be about the same. All right, so now we can switch to the last question. I only got one worked out, so I'll just kind of show this one. All right, so for this one, I'm not gonna just read out all the stuff here. I will actually go step by step in the class, so this way it's more interactive. All right, so we'll start with mousepad. But before we go any further, how did you guys do? Because I still haven't got a chance to look at everything. You think you did okay? Kind of? Okay.
I can't remember what I wrote on the test.
That happens to me a lot.
I'm scared, you know.
Yep.
What made you decide, for the test we were talking about, you were going to give us lines and that's still on the last 3 lines? What made you decide to change to where we were doing the whole thing?
I made the traces kind of short enough to do that. In other words, if you look at this one here, this one has like 3 lines. And the other one is a little bit longer, but that was necessary so I can tell whether people know at the end of a loop you have to kind of go back. So I will still be looking for evidence that people understand this particular concept versus that particular concept. It doesn't change the grade, per se. In other words, people who understand a particular concept will still get points for it. It just makes it harder for myself to look for that evidence because it's no longer a single answer, that I can just say 100% or 0. I now have to go to each concept and go, okay, is this person demonstrating an understanding of this concept? And I have to go through the trace to find that. All right, so going back to, nope, not this one. And okay, there we go. All right, so the first thing we have to do is to go from post 5 all the way back to pre 3. Okay, that's what the question is asking. What is pre 3 once we know this is what post 5 is? Okay, so going to this, using a step-by-step approach, this is what we're going to do. So I'll just restate what is post 5 just because it is important. In this case, post 5 is x equals 4k, y equals m, and z equals 5. In other words, I know as a fact that every time we get to line 5, right after we execute line 5, this condition has to be true. But what is the value of k and what is the value of m? I don't know. I just know that they have a particular value, and x relates to k by the first equality, y relates to m by the second equality, and that's all that I know, which is okay. So there's no need to really know the exact value of k and m because I only care about the relationship between the variables. Are we doing okay so far with that concept? There's no need to know the exact value. We only want to establish the relationship between the variables. Okay, so knowing that, without using pre-post condition, without using the forget and the substitution operation, is there an easy way to explain what pre-5 should be? In other words, if I know that this condition has to be true after line 5 executes, is there anything I can say about what has to be true right before line 5 executes? Well, let's look at these pieces one by one. Go ahead.
Should it just be post 4 as sequential?
It is also known as post 4, but I'm just going line by line, so I'll establish that link here a little bit later. Yeah. I know your point. Can we keep this part?
Yes.
Yes.
Because line 5 doesn't do anything about k nor x, right? So if after line 5 x equals 4k, wait, that has to be true before line 5 because we didn't do anything about these two variables. And then the same thing applies here. So the last part is, can I still say something about z before line 5?
No.
We cannot say anything about line 5 we cannot say anything about z before line 5 because it is not a reversible operation. Yep, go ahead.
Can you just say it exists?
Sorry?
Can you just say it exists?
You can say that it exists, but there's nothing else you can say about it. So if in your answer, if you just say that z is a variable that exists, I won't take any points off as long as you don't say anything more specific than that. Yep.
Just in theory, like on the whole thing that it exists, could you assign a new variable to it that we have to define? Because
that depends on the language. In other words, that becomes a language dependent kind of thing. Because this class is feeding into C and C++, where all variables have to be declared before they get used.
Okay.
So what he said has to be true as well, because in order to get to z, and there are no variable declaration in between, so that's why z has to exist before line 5 as well. Now, when you're talking about an interpreted language like Perl, PHP, and stuff like that, then even that cannot be claimed, because the first time you use a variable, it just comes into existence at that point. Yeah, so point well taken. But in this case, I can accept both as correct because it is language dependent. So, but the most important part is we can no longer claim that z has an exact value of 5. That's the whole point. Okay, depending on the language, you can say we may or may not be able to confirm that z at least exists at that point, but that's okay. That's kind of besides the point in this case. So after we know what is pre-5, then we can establish what is post-4, because post-4 is the same as pre-5 because those two lines are next to each other. They are sequential. Okay, they're not just following each other in terms of line number, but they are sequential. Now this part here is not something that you have to write, because you just have to tell me what you think pre-3 is, and then go forward to prove that it will lead you to the post-5. So this is what I just want to illustrate, because I want to show you the rationale behind all the derivations. All right, so now that we know what post-4 is, let's see if we can say something about pre-4. Because post-4 is the same as pre-5, which in this case is just knowing that x is 4k and y is m. That's all that we know. So let's take a look at line 4 here. Line 4 says y gets y plus 1. What is that effectively doing to y? Is incrementing y by 1. Okay? So knowing that y equals m after line 4, can we say something about y and m before line 4? Yep. Okay, very good. So you guys all got this part. So before line 4, without using substitution operations and stuff like that, we can intuitively just say that y equals m minus 1. If you say y plus 1 equals m, it's just as good. Okay, as long as it is stating the same thing, it's fine. Are we doing okay up to this point? Because this is where we can say, oh, we don't have to toss that away. We just kind of change it a little bit, and then we can still say something about y and m. Yep.
I did the y equals m minus 1, but does it matter as long as it says equivalent statement?
Exactly. As long as it is the same statement, you can use algebra any way you want to kind of put things on the one side, put it into different sides. You can even say m minus 1 plus y equals 0. Excuse me, m minus 1 minus y equals 0, because it really is saying the same thing.
Y plus 1 equals 1?
You can say y plus 1 equals m. Yeah. All right, so that's done. We just have to establish the connection to the previous line, which is line 3. Post 3 is the same as pre-4 because they are sequential. I'm just restating, what we already know. All right. So the question now is, knowing that after line 3 executes, we know that x equals 4k and y equals m minus 1. Can we say something about the variables before line 3 executes? What do you think?
X equals 2k.
X equals 2k, or you can say 2x equals 4k. 2x equals 4k is saying the same thing, and y equals m minus 1 does not get changed because line 3 does not affect either y nor m. Okay, so are we doing okay so far up to this point? This is not what you need to show in your answer. What you need to show in your answer is just that part. Okay, the rationale to go back up to pre-3, you can just do it intuitively, but to go forward again, you have to use the derivations that we talked about in the class. Is any one of these steps kind of fuzzy, or do you want to talk about any one of these particular steps? This is all kind of okay. It's all okay? All right, so going forward, we'll be using the pre and post conditions and in explaining why you use a particular rule. So we start with line 3. Okay. What is the first question that we ask in order to determine to use the forget rule or the substitution rule?
Right.
Does it have an inverse? But to have an inverse, we have to confirm something else first. The right-hand side has to contain the variable on the left-hand side. Okay, very good. So we can say in this case, the right-hand side of line 3 refers to the left-hand side, and an inverse exists. Now, when you claim that an inverse exists, you have to tell me what it is. You don't have to prove that it is an inverse, but you have to tell me what it is. So in this case, if the function on the right-hand side, if f of x is x plus x, then the inverse function, which I would use f prime to denote it, is going to be what? What is the inverse? X over 2. Yep, that's it. Okay, x divided by 2. All right. So because an inverse function exists, we can now determine that we should use the substitution rule. The substitution rule says it relates the post condition to the precondition using the substitution operation. You have to tell me which variable is being changed. In this case, which variable should be changed? Should be x, and what are we changing it with? Changing it into f prime of x. Okay. So the next line is just to expand it. To expand it, it's easier here because I can use copy and paste. And that's x divided by 2. And then the last step is really just to do the substitution. The substitution will end up as 2x equals 2k. No, that's not true. X divided by 2. And y equals n minus 1, because there's no mentioning of x whatsoever here. So the only substitution I have to do is over here, change it into x divided by 2. If you leave it like this, it's good enough. There's no need to kind of change x divided by 2 equals 2k to x equals 4k. If you do that, it's good. If you don't, it's no problem. Are we still doing okay so far? Yep, go ahead.
So what if you screwed up and used the
How?
instead of the sum?
Okay, which part did you screw up?
Oh, I wasn't paying attention and didn't do the inverse thing. I used forget instead of sum. So how does that screw up the entire thing?
I do it step by step. In other words, if you get this step wrong, but the next step is consistent with your mistake, and it is actually done correctly, you still get partial credit for the next step. Okay.
Theoretically, how would the forget rule alter this algorithm? I mean, so you would forget
You cannot use it.
Okay, I wasn't sure if there's a way you could have.
The forget rule basically
forced
says
to
you are
work.
just forgetting everything that you knew about x, but then what are you going to state after that?
Yeah. And even if you do get 2x, it's like, well, you have 2 of something unknown.
Right.
I didn't have this one. I was just kind of curious. In
Yeah.
theory.
Yeah. These things are really simplifications of what we call algorithm verification. So by the time you get to that class, which is an upper division class at a 4-year university, they will present the same material but in a very different way. These are very specialized. It doesn't work in some cases. Because if you look at the forget rule, we are forgetting more than we need to in some cases. But these are very easy to apply because they're very rule-based, very mechanical, and that's why I kind of use this method in this class.
Okay.
Yep. All right, so this is post 3, and then we just say pre 4 is the same as post 3 because they are sequential. You don't have to say that because they are sequential, but I would like to see a connection from line 3 to line 4, because otherwise, how can you get started with line 4 if all you know is about line 3? Okay, so now the line 4 is pretty much the same thing. The right-hand side of line 4 refers to the left-hand side, and an inverse exists. In this case, In this case, this is y, f of y is y plus 1. So to inverse, or to reverse that, you have to subtract 1. Are we doing okay so far? Now, to be much more complete, I would, go and prove that the inverse works. In other words, if you apply f prime to y, excuse me, if you apply f prime to f to y, you get y back. Okay, because that's the only way to basically show, yes, this in fact is the inverse function of that function. But in this class, in an exam like this, if you just tell me what is the inverse, it's good enough. Because these are pretty intuitive. They're not very difficult. Okay, so post 4, once again, is the result of applying the substitution rule to pre 4. This time we're looking for occurrences of y. And with each occurrence, we want to replace that with the inverse function applied to y. And this part is just expanding what we already knew about pre-4. Pre-4 is the same as post-3, so I would just copy and paste this. Replacing y with y minus 1. Yep.
Before you go too much further, so the step before, what if you just simplified it? Like you simplified x over 2 equals 2k to simplified it down.
That's fine.
Okay.
Yeah, that's cool.
That's
Yep. As long as it still states the same relationship between x and
says
k.
that, and below it, it's just simplified.
Yeah, that's fine. No problem. So in this case, I would just say y minus 1 equals m minus 1. If you leave it like that, it's good enough. Okay, if you take it one more step and just say y equals m, even better, but no extra credit for that. But they're the same, right? As long as you're stating the same facts, the same conditions, the same statements, it is okay. Okay. All right. So I'm just doing the minimum mechanical steps possible to get all the points. Okay. Is it mechanical at this point? The only part that is not mechanical is to figure out the inverse functions. But the inverse functions in this case, on both line 3 and line 4, I would say they don't really need a lot of effort. I hope that is true. Okay, we're down onto line 5, so we have to say pre-5 equals post-4 because those two lines are sequential. You don't have to explain they're sequential because in this case it's obvious. But you still have to say the right-hand side of line 4, line 5 in this case, does not refer to the left-hand side because that is the reason why we pick the rule. So we have to say use the forget rule. Forgot to state that over here, so we have to do the same thing. Use the substitution rule. So in this case, we use the forget rule. The forget rule, says something like this: the post condition of line 5 depends on the precondition of the same line. We have to get rid of certain things, so we have to say forget whatever is in pre-4 that mentions any pre-5 that mentions anything about the variable to be changed on line 5. And what is that? Z. Okay. And after the forgetting, you can say one more thing because we know what the assignment statement is talking about. So z equals 5 has to be true after line 5. So now we expand everything. Pre-5 is this mess here. You just have to copy it. And is there anything to forget? Did we claim to know anything about z before line 5? No, we didn't claim to know anything about it, so there's nothing to forget. So that means after the forget operation, we get everything back. There's nothing lost. But we got something to gain because we also know z equals 5 after line 5. And that's it. That's the whole answer to question number 4. And remember, parts of this, you don't have to use either. This part here, this is all extra stuff that I want to show you, because I want to show you how I would figure out the preconditions step by step. But going forward, I would say this is the minimum to get the full score. In other words, I'm looking for the rationale why you choose to use a particular rule instead of the other one, and also the mechanical steps to apply those rules. You can probably skip one line and I will still be okay with that. Like skipping this line is okay because we already know what is pre for, we already know what is f prime of y. If you skip this step and go straight to this one here, it's okay with me. All right. Any questions about the exam? So once again, I'll be grading it, looking for evidence of, the understanding and application of a particular concept. So when you look at your grade, you will see, instead of getting just point values, you'll basically see a breakdown of concepts that you need to know for this exam, and then a rating of those concepts. So you will see multiple numbers per question. Yep.
Do you have a rough ETA on when we'll be getting our exams back?
Well, I'm pretty sure about how I can use the tool in Moodle. So I think Thursday is very realistic.
All right.
Yep. So what do you guys think? Was it an okay exam? It always does. It always does after the exam.
It's the wrong time for it to make sense.
I would not say it's a wrong time. There's always the final exam. So understanding now is okay. I mean, this is 20% of your final grade, which means it's only 20%. So this is a good time to realize, hey, I didn't get a very good understanding of this material, because guess what? You can go get those points in the final exam. Yep.
So honestly, I didn't see two impossibles coming on the last one you did.
Oh, you can have any number of impossibles.
I got the first impossible, then when I got to the second impossible, I was like, no way he's making us do two impossibles, he only showed us how to do one.
I did not use any really tricky
I
ones.
just didn't answer it.
Yeah, let me show you what would be a tricky one. The objective, is not to trick you guys, so I don't have to give out any A's, because I don't have to. It's not like cookies, right? It doesn't cost me anything to give out, a good grade. If it's cookies, I might actually try all the tricks and make sure that nobody gets an A in this class. But it's not cookies.
Trying to answer it probably. I've spent too much time trying to answer it when I knew in the back of my head it's not.
Yeah,
gonna work.
well, time allocation and second, guessing yourself is something that you have to. Everybody will have a different way to do it. Now, if I were to make this really tricky, well, I wouldn't say really tricky, but kind of trickier than what it is, I can do something like this. Okay, so instead of using this, I can do something like that. Okay, that will make line 2 impossible. Z equals 1 becomes impossible right off the bat, right? But it doesn't change the other ones.
But you
Okay.
can never enter the condition.
I can never execute line 2, but line 4 is still possible. Line 6 is still possible. Line 8 is still possible. In this case, line 10, well, let me see. Line 10 would not be possible, would still not be possible, because the greater than is covered by not equal to on line 7. But this will be tricky, because right off the bat, the first one is impossible. But just because it is impossible doesn't mean the other ones are also impossible. Okay. I can turn this into something that's even trickier, and change that to a OR. Now that would be tricky, because what does that mean? How would that change the answers? It means Z equals 1 is still possible, and you can choose anything for X, you can choose anything for Y, but all of the other cases will be impossible. Every single one of them. Yep, 2, 3, 4, 5, and 6 will be impossible. Because the first one is true regardless of the values of X and Y. So that means it is impossible to make line 3, 5, 7, or 9 true and at the same time making line 1 false. If it is not possible to make line 1 false, then you don't have to, all the other cases are impossible. So I would think this will make it tricky. I would call this a little bit tricky, but the way it was, I think it was okay. Not acceptably
You
tricky.
could put more conditions on the other lines too.
In the other ones?
You could, you could say like x equal y and y doesn't equal this.
Yeah, but that makes grading very hard too. I don't want, well, for grading, I can actually make my own macro, so I can plug in your value to make sure that my scoring is correct. So that part I can actually make it fairly automated. All right, so any questions about this one? Yeah. Okay. So that was the first exam. And as I said, each one will have partial credit. I think that the nice thing about question number 3 is, even if someone is missing, this case, z equals 5 is actually the trickier one. The first 4 are fairly okay, I think. So you will still get, most people will get, a good amount of partial credit, if not everything for question number 3. All right. So are there any questions? Does anyone want me to remind you of the letter grade equivalence of this class, which is not the usual that you see? Nobody?
Yes, can
You guys
put it on
already
board,
know?
please?
Huh?
Can you put it on the board, please? Or show us?
Yes, because I can always go back to the syllabus. How many people have clicked the syllabus after the first week or so? Okay. How many people click it only after exam 1? Don't need to know that. Oh, wait, I do need to know it now. So this is the breakdown. So anyone who gets less than 12.5% of all the point values will get an F. I think that's pretty fair. Right?
You almost have to work for that kind of low. Technically, try to A on the first
Still have
test
people-
and the homework, you already have a C.
Sorry?
If you got it like 100% on the first test and did the homework, you probably already have a C.
Yep. Yep, pretty much.
Or a D.
You still have people fail the class.
Now people who, okay, if someone, let's say if I take this test and I flunk, the first exam like completely bombed out, okay, I got 0% out of it, that will make A impossible for me, okay? I cannot get 87.5% anymore. But what about B? Does it still look kind of okay that I can get a B out of this class? Absolutely. Okay, so so that's basically how I would look at it. Is if I miss this one test, exam 1 completely, I will still have a chance to get a B out of this class. Yep.
So it's like relating to grades on Moodle, where the grades are.
Those are all kind of fuzzy. I haven't really assigned the
so
right
bottom
categories.
It says you still have an F, and I was like, I'm done.
No, that has not been adjusted correctly yet. Because all the homework assignment add up to only 20% of the grade. The first exam is 20%, the second exam is 20%, and then the final exam is 40%. So you can look at it the other way, like turning in none of the homework assignments, bomb out both exam 1 and exam 2, ace the final exam, and you can still walk out with a C in this class. As I said, nobody has tried that before. Well, okay, I take it back. Maybe somebody tried, but nobody has succeeded yet. You were doing that. I have had people who missed the final exam because they got enough points, and they might have more important tests or something else. I don't really know or want to know why they did not come to the final exam. There can be so many different reasons, but they got a passing grade, and if that's good enough for them, hey, no problem with me. All right. So that's the first test, and then here comes the top-down design stuff again that we talked about. We started to talk about this before exam 1, and today would be a good time to continue to talk about it. All right. So So let's go ahead and think about factoring prime numbers out of a number. Last time we kind of proved that we only have to go up to the square root of a number to try to find a factor for that number. Because if I cannot find a factor, by the time I get up to the square root of a number, I can confirm the number as a prime number, and therefore I don't have to search anymore. Okay, that's what we found out last time. So this time we want to finish up the entire algorithm, because what we originally wanted to do is not to find a single prime factor out of a number. We want to find all of the prime factors out of a number. Why would someone be interested in that sort of thing? How can that be useful? In other words, let me give you an example. I want to look at, let's say 84, okay? I want to look at this as, oh, okay, I know 2 is a factor because that's an easy one. It's 2 times 42. And I look at this and go, well, what about 42? Well, I know 42 is a composite number. It is the product of 2 prime numbers, or two or more prime numbers, I should say. It is 2 times 21. I look at 21 and go, I think it's divisible by 3. And then I look at 7, and 7 turns out to be a prime number itself, and so I can no longer factor anymore. The only thing left is 1, but 1 is not even a prime number, so I can stop at this point. Why is this process useful? What do you use it for?
You use it for like substitution?
Go ahead.
No, it's just when you have square root in
When-
mathematics.
In mathematics?
Easier for factor crap out.
Yes, factoring the crap out of something. Yep. And why do we need to do something like that? LCM and GCF. Yep.
That way you can figure out different forms of it, so you can restate it in different forms to get it to fit in the basket you're trying to fit.
Yep. As I said, LCM is one application, and GCF is the other application. How many people still remember what is LCM and GCF? I'm impressed. Because I would think that most of you, because you don't have to use it in your daily life, you would have thrown those things out of your mind. Do you guys have kids or younger people that you have to teach that stuff to, and that's why you still retain that knowledge? No? Okay.
I just like to keep useless shit in my brain.
Well, okay, as I said in the previous class, did I say in this class or the previous one? I think I said it earlier in this class. The more you know and the more you can connect everything that you know, the easier it is to remember everything and actually learn new things at the same time. So all that quote-unquote useless stuff is actually increasing your capacity to know even more stuff. So there'll be more useless facts in your brain later on. But you can retrieve every single last one of them.
Right up until you reach the actual limit of your brain.
Then you have to hit that reset button called the baseball bat. All right. So this is actually useful because GCF stands for greatest common factor, and LCM stands for least common multiple. Well, at least that's how I learned it. There may be other ways to refer to these things. Okay, and we use these for simplifying fractions. Okay, that's one of the biggest applications of these things, is to simplify fractions and figure out multiple. There we go.
Don't they use prime numbers when testing processor stability?
Prime numbers are extremely useful in cryptography.
Well, I mean, just with day-to-day stuff. There's a program called Prime 95, and you use it to
Right. They use it as a benchmarking program.
Right.
Only because it is compute intensive, and it exercises enough of the commonly used features of a processor. You can always design a benchmark test that will only exercise certain parts of a processor, which makes it easier for manufacturers to claim a really high score in a benchmark test, but in reality it's not really high performance. So the Prime 95 program was there to begin with, okay? Somebody wrote it already, and it exercises enough parts because it has division, mod, and testing and loops and stuff like that. So it was just a good test of a general test for the performance of a processor. Okay.
I have
All
a
right.
question.
Yep, go ahead.
Why are prime numbers important to cryptography versus any old number?
Well, let's take a look. So all you have to do is to look up prime numbers, okay, prime number, and then you look up cryptography. That. And why are primes important in cryptography? Exactly the way you phrased it. One thing that always the number theory, all integer numbers are made out of primes. So you do the RSA, which is a particular, RSA refers to the agency, is the name of an agency, but they use a particular way to do encryption or key pair encryption. And they use prime factorization of large numbers because that takes a large number of time, a huge amount of time, and that's why they use this method to do key pair encryption. You have a public key which consists of a product of two large prime numbers used to encrypt a message, and a secret key, which is a private key, consists of the primes to decrypt the message. You can make the public key available to everybody, but then the other key you have to hide. And then you can read the other answers. And that pretty much explains why prime numbers are useful in cryptography. Basically, what it says is one thing. If you have a magical box and you can throw any huge number to it and it can instantly give you the prime factors, all existing cryptography methods will be useless.
Which is what's going to happen when quantum computers get up and running.
That might take a while.
Well, I know they have a small one. It's not small, it's quite large, but like a low-powered one.
But the programming part of it is really difficult because it behaves very differently compared to what we call, von Neumann, machines, but they're deterministic. Because quantum computers are not deterministic, that really makes writing algorithms a whole different experience.
I remember reading that they did some testing with protein folding, which is like one of the most computer-intensive tasks like ever, and it actually had some good results, like better than any computer they tried on. So
That's something to take a look at.
When I get home, go see if there's anything.
All right. Well, that's good to know. Let's take a look at another example. 196. I want to factor this into its prime components. Okay. Now, the reason why we want to go through these exercises, a few times, is to see whether there is a way to systematically solve the problem. Okay. Anytime you have a systematic way to do something, chances are you can write an algorithm to do it. But for certain things where you do not have a systematic way, or you cannot describe the systematic way of doing it, then it becomes much harder to write an algorithm so a computer can do the same thing. Yep.
Talking about like using bisection.
Bisection.
Dividing by 2. Like
Dividing.
it's how you can guess. It's easy to guess a number between 1 and 100.
Right.
Because you divide by 2. So you say 50.
Assuming the feedback can tell you whether the number is equal to, greater than, or less than the target. Yes. Because if the feedback is only yes or no, this is the number and this is not the number, then you cannot use that technique. You basically have to go sequential or just go random because it doesn't make any difference in that case. Okay, this is 192. So 192, I can identify 2 as a prime factor. So once 2 is identified, we have 2 times 98. Now we only have 98 to deal with. 98 obviously has 2 in it too, and it is 2 times 49. 49 is 7 times 7. But I have to go one step further because I have to look at 7 by itself and realize that 7 has no prime factor other than itself, and then we are done. This is not really so good of an example because here we identify 7 as a prime factor already, but we have to be systematic. We look at whatever is remaining, which is the quotient of 49 divided by 7. We look at the quotient and then we try to apply the same thing here, except in this case, 7 cannot have any other factor than itself. So the remaining portion, which is the 1, this one is the quotient of 7 divided by 7. So when the quotient of the division becomes 1, I know I'm done because there's nothing else to do in this case. Are we still doing okay so far with this example? You can try something that's really redundant, like 128. 128 is 2 times 64. 64 is 2 times 32. 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4. 4 is 2 times 2. And 2 is 2 times 1. But by the time we get to 1, we're done. Can everybody see how the 3 numbers on each line relate to each other? I'll just pick a random line. Pick this line here. Okay. How are these numbers related? 98 is, well, it says right there, 98 is 2 times 49, but what is the other way to look at this? 49 is the quotient of 98 divided by 2. And that becomes the number on the next line, because that's the number that I want to factor. Now this pattern continues all the way up to the last line, because on the last line, in this case, 7 is 7 times 1, which means 1 is the quotient of 7 divided by 7. Okay? So that's what we are looking for, is a particular pattern, a particular regular, systematic way of doing something. I'm not trying to apply special rules. Okay? I'm not looking at, I'm not looking at this and go, oh, okay, I can see that 128 is a power of 2, and I just randomly pick, oh, it is, well, let's see what it is. It is 8 times 32. No, it's not 8 times. It's 8 times 16. Okay? I don't just pick some random number as factors and then apply, oh, okay, I choose to factor this side of it first, and then I choose to factor the other side. I'm trying to be very consistent. Okay? The other thing that I was also trying to do here is with 196, I did not try to identify 7 first and then the 2. I'm going from low number to higher numbers. So given this little demonstration, do you think we can have a systematic way to factor out all the prime numbers out of a particular number?
If you have a list of prime numbers to use.
Well, we don't need that. That would make it efficient, but it's not necessary. Okay. Okay. Let me just kind of repeat your question. The question, not the question. The point was, I could use a list of prime numbers, and the answer is yes. If I have a list of prime numbers, it will make it efficient, but I don't really need that. Remember last time, what algorithm did we talk about last time before exam 1? It's an algorithm to find a single prime factor of a number, right? It wasn't really efficient because I was testing 2, 3, 4, 5, 6, 7, 8, 9. There are numbers that I really should not be trying, but it doesn't give me a wrong answer. It works, okay? So in this case, we'll just kind of use the same philosophy, and then we'll try to see if I can come up with an algorithm to do it. And this time, it will use the concept top-down design. Okay, so as usual, what I usually do is you look at the process, and then you think about it, and you say, is it a repetitive process? Am I doing some operation again and again? What do you think? Does it seem repetitive to you in a certain way? Okay. Okay. If it is repetitive, we just say that, right? Okay. There's some kind of a loop. I don't know whether it's a pre-checking or post-checking loop, but there is some kind of loop here. And when do we get out of the loop? Because every time you have a loop, you have to determine, is it supposed to be an infinite loop where it does not end ever, or is it supposed to get out at some point? Yep.
When the remainder
Is not zero. When the number still can be factored, right? Okay. So we'll just say that we exit when there is no factors left. How's that? Okay. So that seems reasonable. In fact, we can say for each iteration, we just say extract one prime factor. Okay. Now, obviously, if you just look at this revision here, I'll call this revision 1. Revision 1 is not very helpful. Okay, if you key that, you type it into any programming language, no program can recognize and figure out how to do this. But to us, it is important because it identifies several things that will be very important later on. 1, it is a loop. 2, the loop is supposed to end at some point. And 3, it is supposed to stop when there are no more factors in the number that we are factoring. Now those are all very important things. We just have to figure out how to restate all of those things in a way that is specific. All right. So in revision 2, we just say that this is really kind of fuzzy because what is the number being factored and what is the prime factor and stuff like that. So now we want to use names. Okay, we want to use variable names to identify different portions, all the different numbers, the values that we are dealing with. So we say assume n is the number being factored, and we can say assume f is a prime factor of n. That's all I'm going to use here. And then we can try to restate the loop here, but using these terms. Can I change only this part here, where it was, there's no factors left? How do I restate that once that I have these terms? Would that work? When n equals 1, it cannot have any factors. Okay, all right. And we'll just, use this, as revision 2. Save the file to today's folder.
It's up at the top.
Nope, because I sorted by modification time. All right. So now let's try revision 3. Revision 3 is going to take this, and then we have to figure out what we have to do. Do you think I'll have an n that equals to 1 as the problem to solve all the time? So n usually would be a number greater than 1, right? It's going to be 196, 49, 128, and so on and so forth. So if n is the number being factored and is given to me and it's not 1 to begin with, or at least not all the time, that means whatever I do here has to affect n so that eventually it becomes 1. Does that make any sense? Yeah. Because if n equals 1 is the exit condition, I want to make that true at some point. But to make that true at some point, that means I have to do something to n inside the body of the loop. Okay? So we'll go ahead and take a look here. So we know one thing for sure. Okay, we know that we want to do something that looks like this. N gets n divided by f. Because what f is a prime factor of n. Is that okay so far? Okay. But then before this, we have to say that, but how do we find f? Well, there are two things to do. Assuming that we did not talk about the other algorithm to find a single prime factor given a number n. Let's say we haven't talked about that yet. Okay. What I would do is I'll just be lazy. Okay? I'll make a very bold assumption and say, well, I'll just assume that somebody else has already figured this part out. Okay? So instead of stating the algorithm to do it, I'm just going to say something like this. Find a prime factor f of n. Don't ask me how to do this. I'm just assuming that somebody else has already figured out how to do it. Is that okay? That right here is top-down design. Why do you think I just call this top-down design? I'm leaving. Yep, go ahead.
You start at the top level, the top ideas, and you go down and get more specific at each step.
Exactly. I'm leaving out some details. Okay, I'm saying that I can only track so many things at the same time. If I just say that I'm assuming that this algorithm exists and somebody else has done it already, I now can focus on just these several lines of code instead of drilling into the details as I'm trying to write this. It's just like in the process of writing an English paper, you're basically just using a placeholder to represent an entire section of your English paper and say, okay, this chunk is going to establish the background of my argument, of my point of view. Okay? I'm not going to spend the time to drill into it yet because I want to focus on the general overall structure of my entire English paper. It's the same thing here. I'm just saying that I don't want to deal with the details of doing this. I just know that this is what I want to do. In other words, it tells me what I want to do, but not necessarily how to do it. Is that okay? So top-down design has a lot of this kind of stuff. It is focusing on what we need to do, but not how we can do it. All right. So we'll just leave this one, as revision 3. Now we can move on to revision 4. Revision 4 is going to try to make it a little bit more specific. And also in revision 3, we'll just go ahead and say print f, okay? Because we have to generate the output, to the end user, so the end user can actually see all the prime factors. Okay, we only have one thing left to do. Should I turn this into a pre-checking loop or a post-checking loop? In other words, should I say repeat until n equals 1, or should I say while n does not equal to 1, do da 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 da? Okay, well, let's take a look at both approaches and then we can talk about it. Revision 4a means we will use, let's say, repeat until loop in this case because that's the easier conversion. To convert from a loop and loop to repeat until is really just syntactically changing repeat as the beginning of the loop and change the end of the loop as until. So that's one way to do it. The other way to do it is to use a while loop. In that case, we have to invert the condition, but then we can keep everything else in between. This is revision 4b. So let's take a look at revision 4a and 4b and see which one may be a better choice. If I tell you ahead of time and say, well, guess what? The user may enter n as 1. Then which one should I pick? While, exactly. Okay, if I tell you that the user may give me a value, a number to factor, and that number may be 1 itself, I have no choice but to use 4b, because what happens when I try to use 4a when n can start with a value of 1?
It's not optimized or whatever for that.
It won't work. It simply won't work because what is a prime factor of 1? There is none. Because 1 is not a prime number. Okay? Remember the algorithm that we talked about? What if n has a value of 1 and we apply that algorithm?
Gives you a bunch of 1s as the answer. If
No.
1's a prime number.
Sorry?
You can't use 1 as a prime number, so it just gives you a bunch of 1s.
1 is not a prime number, so it will give me a result of f equals to 1 because of the optimization. Now without the optimization, it will not exit. Okay, so this is a good time. Well, we got 2 minutes. It's enough time to go back and review it. The simplest form of the algorithm to find a prime factor is to initialize n to f to 2, and then we say while n mod f does not equal to 0, do f gets f plus 1, and while. This is without the optimization. In this particular case, what happens when n equals to 1? Let's just kind of go through a few iterations and see if we can find a pattern. If n equals to 1, in the first iteration, it will say n mod 2. What is the value of n mod 2, or the remainder of n divided by 2? No, it's 1. The remainder of 1 divided by 2 is 1. So should I stay in the loop? Okay, the condition is true. I stay in the loop. I add 1 to f. F becomes 2. F becomes 3. What is 1 mod 3? The remainder of 1 divided by 3. No. It's 1 again, right? So I have to stay in the loop. I add 1 to f. F becomes 4. What is 1 mod? What is 1 mod 4? 1. 1 mod 5. 1. 1 mod anything other than 1 is 1. So this loop will never exit. So we'll be stuck in this loop. Now, in the other case, once we have the optimization says something like this. It says, we have to stay in the loop if this condition is true, but also when f times f is less than n. We stay in the loop, but then we have a condition here that says if f times f is greater than n after the loop, then f is n, because n is a prime number in that case. So what happens after the optimization when n equals to 1? It will exit right away, right? Because f is 2 already to begin with, because that's how it's initialized. 2 times 2 is 4. 4 is less than 1 is false. And this is a conjunction. That means I will get kicked out of the loop without going through it even once. The conditional statement will say, oh, 2 times 2 is greater than 1, so the condition is true. So f will end up with a value of 1. But that will still be incorrect because 1 is really not a prime factor of 1. 1 is not a prime number. How do I know that 1 is not a prime number? Because I looked at Wikipedia.
Because what?
Because I look at Wikipedia. Well, because it is by definition. It is by definition. There's no particular theorem to prove that 1 is not a prime number. It is just by definition.
Because it's not divisible by another number itself. It's only divisible by itself. That's the definition of a prime number.
Well, this is what Wikipedia has to say about it. If you don't agree, you can always change it, right? Because it is Wikipedia. A prime number is a natural number greater than 1, right there. Means that 1 cannot be a prime number. Okay? So, let's see. We still have 3 seconds. Okay, going back to this algorithm, we have no choice but to choose revision 4b. Okay, that's it.
Excellent use of those